Recording.
Good afternoon. It's a pleasure to introduce Professor Claudio Alves from Federal University of Campina Grande, with over 13 publication articles in more than 1,000 citations. He was significant contribution in this field. Professor Alves is also supervisor of numerous PhD thesis and master dissertation. The topic of this presentation is on the instance of normalized solution to the smooth class of elliptic problem. Please.
Okay, thank you very much. I would like to thank the organized committee by invitation, by opportunity to participate in this meeting. And for me, it's an honor. And today I will talk a little bit about the existence of normalized solution for some class of elliptic problems. And here I show for you the plan of my talk. Okay, probably I will not talk about all these themes because the time is not so large. And here I show for you the two problems that I would like to talk. The first problem one, is one problem involving one bound and domain. And the second one is one problem involving one elliptic problem in R2, in whole Rn. And I would like to emphasize that in this talk, I would like to prove the existence of normalized solution. And normalized solution, we understand one solution that the L2 norm is prescribed, okay? And here I will talk about two classes of problems, L2 subcritical and L2 supercritical group. Later on, I will show for you the definition of the L2 subcritical and L2 supercritical group. When the dimension is equal to 2, our result permits that the nonlinearity has one critical exponential group in the true Degemoser sense. Involving the problem 2, and we will suppose that the potential V is bounded, positive, and Zn periodic. And the both problem in the bounded domain, problem 1, and the second problem in whole Rn, our nonlinearity is one continuous functions, okay? And the both problem, when we are working with the dimension 2, we can consider the critical exponential group because this type of group is the natural for this dimension. For this class of problem, the number A that appear here involving the L2 norm is fixed, while the number lambda that appear in the right side of the equation is one null parameter. This null parameter appear when we apply the Lagrange multiplier. The results that I will show for you in this talk appear in one paper that I wrote with my colleague from China, Li-Jun Shen, okay? And what is the motivation to consider normalized solution? Okay, when we studied the nonlinear Schrödinger equation, in the previous talk, our colleague Luis talked about the preservation of mass. When we study the nonlinear Schrödinger, we would like to find
Your audio, Professor Claudianor.
Yeah.
Hola.
Yes, excellent.
Probably can you hear me?
Yes, it's okay.
Okay, and in the nonlinear Schrödinger equations, sometimes we would like to find solution with prescribed mass. And here in the equation 3, we have one type of nonlinear Schrödinger equation where omega can be bounded or unbounded. So one special class of solution for nonlinear Schrödinger equation is one solution like the red solution. When we try to find one distinct wave solution and we put this function in red in the nonlinear Schrödinger equation, the equation 3, we get one new PDE, more precisely, one elliptic PDE. PDE is the PDE 4. Okay, so in order to find standard wave solution, it's enough to find one solution for problem 4. If you can fix lambda, okay, if you can choose lambda, you can try to find one state wave solution by finding critical points of the energy functional I lambda. For example, if you choose lambda, one negative lambda, this functional is strongly definite, and in a lot of cases, you can find critical points by minimization or by using mountain path geometry. If you fix, for example, lambda positive, you has one limp geometry. And of course, in this case, this geometry, it's not so easy to work. So if you want to find one standard wave solution and you can fix lambda, it's well known in the literature. But the main point is when you try to find one solution with the L2 norm is fixed. In this case, you cannot choose lambda. Lambda is part of the unknown. Why this type of solution is important? Here, I recall again, in the physical point of view, we have the conservation of mass. So you have one solution of the nonlinear Schrödinger equation. There is one law that say that the L2 norm of the trajectory is preserved. Also, that is, the L2 norm in any time t is equal to L2 norm at the time t0. Okay. Here, I show for you some references involving the existence of normalized solution when the domain omega is whole Rn. This type of problem is so interesting because in a lot of elliptic problems, it's more difficult to find one solution when the domain is whole Rn. In the most part of the elliptic problem, when the domain is bounded, it's more easy to work. But here it's totally different. In Rn, we have a lot of results, but we have a few results when the domain omega is bounded, okay? And here we recall for you the three classes of problems that appear when we are studying the existence of normalized solution. We have the L2 supercritical, L2 critical, and L2 supercritical. I will show for you what is the motivation to divide into three classes the problems involving the normalized solution. So, in order to understand the previous classification, let's consider the problem below. And here, look, in the right side, appear 1 power p minus 1. When this power p belongs to the interval 2 plus 4 over n, we say that the problem is L2 subcritical. When the number P is equal to 2 plus 4 over n, we say that the problem is L2 critical. And finally, when the number P belongs to the interval 2 plus 4 over n, 2 star, we say that the problem is L2 supercritical. Here, we can understand this classification when we study the behavior of the energy functional on this sphere here, SA. So I will talk a little bit about the problems involving the situation where the power P belongs to the interval 2 plus 4 over n. In general, the existence of normalized solution, the energy functional on this sphere SA. This sphere is the set formed by the functions u in H1 such that the L2 norm is equal to A squared. The L2 norm is A, okay? However, it's a very surprising when you are work with the L2 supercritical situation, we lost the possibility to minimizing the energy functional on this set. Okay, in this situation, it is necessary to change the approach. And in this case, in a lot of papers, we use or we prove that the energy functional satisfy the mountain pass geometry on this set SA. In some papers, the authors prefer to work by using minimization, but replacing the set SA by the Pohorzaev manifold. Okay, this is a more sophisticated set. So, but this is a very important to say. This approach works very, very well in whole Rn, because in whole Rn, we have a very nice geometric properties, like it's Rn is invariant by translation, Rn is invariant by rotation group. This information helps in some sense to overcome the loss of compactness involving the Sobolev embedding. For example, if you try to use this type of argument when we replace Rn by one bounded domain, the Pohorzaev manifold does not work well, because we know that the Pohorzaev identity on one bounded domain, we have one additional term involving the boundary of the set. This is so bad when you try to repeat or adapt the argument explored in Rn for bounded domain. So this is, in some sense, can be justified why it's so difficult to obtain the normalized solution for bounded domain. When we consider the existence of a normalized solution for L2 subcritical, it's not difficult, it's so easy, and it's a homework. But L2 supercritical, it's a hard problem, okay? And involving the bounded domain, when I wrote this paper with my colleague from China, we found only 3 papers involving bounded domain. 2 papers due Norris, Tavares, Versini, and 1 paper due Pierotti, Versini. And in all this paper, in order to overcome the boundedness of the PS sequence, because the main challenge when we try to use variational methods to get normalized solution is the fact that in this type of problem, the main challenge is to prove that the PS sequence is bounded, because in this type of problem, we will use variational method on one manifold, infinite manifold. It's not easy to prove this when we are work with the L2 supercritical group. In this paper, for example, in the paper do Enoris, Tavares, Versini, they work with one elliptic system, and they assume a strong relation involving the coefficients that appear at the nonlinearity. In the paper, another paper do Enoris, Tavares, Versini, the authors assume that the omega is one ball, because they work with radial functions. While in the paper Due Pierotti Versini, the authors assume a strong hypothesis on the nonlinearity that imply that the energy functional is C2, which permit to apply the Morse theory. So after studying this paper, we decided with my colleague, Li Jun Shen, to propose one new approach to work with a normalized solution in bounded domain. Our idea is to consider one auxiliary problem. In fact, we will consider the L2 supercritical problem, and we will make one truncation, and we will change one L2 supercritical problem in one to L2 subcritical problem. And after some estimate, we will prove that the one solution of the auxiliary problem is in fact one solution of the original problem. This approach permits to complement the result mentioned in the previous slide, because we don't assume any geometric condition on the domain omega, and we not assume that our nonlinearity is C1. We only work with one nonlinearity that is one continuous function. Here, I show for you the general hypothesis on the nonlinearity. Okay, in a lot of papers that work with the L2 supercritical problem, the author assumed that the nonlinearity is one pure power. In your case, it is not necessary. Okay, and then here we assume the hypothesis F1 and the F2. Okay, and this condition F1 and F2 permit to work with the three classes of normalized solution: L2 subcritical, L2 critical, and L2 supercritical. And here I show for you our main result in this paper. In this main result involving the dimension n bigger than or equal to 3, we have the following result. If the part 1, if the nonlinearity has one L2 subcritical, we prove the existence of normalized solution for all mass A. Part 2, if our problem is critical, we prove the existence of normalized solution when the mass is small. And finally, if we have one problem with L2 supercritical group, we prove the existence of normalized solution when the mass is small, and we need to assume this condition F star. Okay, this hypothesis improve the result that we found in the literature. Okay. For dimension 2, our result is totally new because there is no result involving bounded domain when the nonlinearity has one critical exponential growth. And here we assume that our nonlinearity has one exponential critical growth. And here I recall for you the definition of critical exponential growth introduced by Adimut Yadav. And we can find also this definition in very new papers do De Figueiredo, Miyagaki, Ruth. And we have this definition involving critical exponential growth. This definition say essentially that our nonlinearity behavior at one exponential at infinity, okay? And for dimension 2, we prove the existence of normalized solution when the mass is small, okay? So I repeat that the existence of normalized solution for dimension 2 involving critical exponential growth is totally new. And this theorem complemented this fact in the literature. Related to the problem involving whole Rn, we assume that the infimum of the potential V is strictly positive. This is one technical condition because in order to prove a very nice estimate involving our approximation solutions, we need to use this information. So for the problem 2 involving the existence of normalized solution in whole Rn, we establish the existence again when the mass is small enough. And for dimension 2, again, the existence of solution when the mass is small enough. So I will try to show for you what is the idea. I will not show the details of the estimate. No, my intention here is show for you what is the philosophy of our approach. If you like, if you want to read the paper, you can send me a message and I can send you the preprint, okay? So consider the problem 5 here, and we try to find one solution for problem 5 with the prescribed L2 norm, okay, involving the 6. So here again, lambda is one null parameter and A is fixed. So in order to solve the problem, we needed to get one critical point of the functional J on this sphere SA. So here f is one continual function, odd function, and I will divide the proof in 3 cases, of course, involving the L2 subcritical, L2 critical, and L2 supercritical. So for the case where the power p belongs to this interval, the proof is very easy. It's not so difficult, okay? Because it's not difficult to prove that the functional J is bounded from below. And I will show for you why this estimate holds. Because when you use the groove of the nonlinearity, it is possible to get this groove involving the primitive of the function f, using this information combined with the Gladiardo-Nirenberg inequality, we get this estimate from below involving the energy functional J. Look, here appear one power in the right side in red, the power b beta p times p over 2. In order to conclude that the right side is bounded from below, it is necessary that the power in red must be less than 1. So this estimate beta p times p less than 1 implying that the power p must belong to this interval here, 2 plus 4/n. This is a very interesting fact, but this fact is not so new because in one very, very interesting paper by Thierry Cazenave, Pierre-Louis Lyon, this fact was proven in that paper. So now, using this information together with the fact that the omega is one bounded domain, and the fact that the energy functional is lower semi-continuous, you can prove that this functional achieve one minimum on the sphere SA. So I will jump this part. But the critical case is quite similar to L2 subcritical. When you try to prove that the energy functional is bounded from below, appear in the right side of the estimate this term. If you look the number in front of the integral involving the gradient of the function u, it is necessary to prove that this number is positive. In this case, it is necessary to assume that the mass is small, because when the mass is small, this number in front of this integral is positive, and again, the energy functional is bounded from below on the sphere SA, and again, you can prove that the energy functional has one minimum on the sphere SA. However, the problem or the geometry of the energy functional for L2 supercritical case is totally different. It's impossible to get one solution by using minimization argument directly, because in this case, we prove that there is one sequence on the sphere such that the energy of this sequence goes to minus infinity. This lemma say for us that this functional is not bounded from below. So we need to change the argument. Here, I will try to recover the ideas of the L2 subcritical problem. Why? This is our trick here, okay? Our idea is the following. We will make one truncation on the nonlinearity. And our idea is to use the mass as one parameter. And we will prove the following. When we consider this truncation here, and we, in some sense, we are change the problem L2 supercritical to one L2 subcritical problem, because this function f capital R has one L2 subcritical growth. But it's a very important, and I would like to ask your pay attention, because this function fr is equal to the original function ft when the number t lives between 0, capital R. So what is our idea? The idea is the following. I will try to get one solution, okay, for this problem here, and I will use the elliptic estimate in order to prove that if the mass is small enough, the L infinity norm lives in this interval, 0, capital R. This is our idea. For me, it was surprising because the mass does not appear directly in the the problem, okay? The mass does not appear directly in the problem, but the mass, in some sense, has some control on the L infinite norm of the solution. So have this in mind. And we prove that this new nonlinearity satisfies the Ambrosette-Rabinovitz condition. And we can use the idea of the previous session. And we prove that this problem 16 has one normalized solution. And what is our goal? Our goal is to prove the following, that there exists one capital R such that the L infinite norm is less than or to capital R. And in this case, in order to this inequality hold, we will explore, okay, the mass A. We will prove that it's in fact hold when the mass is small. So here, our main goal is to prove that there are R positive and R star, such that if the mass lives between 0 A star, the L infinite norm of the solution UR is less than or equal to R. So here, okay, in this lemma is one technical lemma. We prove that there exists one constant C that does not depend on R, so that it is possible to control the gradient norm, the L2 gradient norm. So using this fact, it is possible to prove that the minimum of the solution is negative. So this number gamma R is the minimum of the functional JR. The functional JR is this functional associated with this problem. So we prove that this number is negative when R is small enough and R is bigger. We use this fact because when we have this number gamma R negative, it is possible to deduce that the Lagrange multiplier is also negative. When the Lagrange multiplier is also negative, and the Lagrange multiplier will appear here in the right side. If the Lagrange multiplier is negative, we can move this term for the left side, and when we apply the Moser iteration technique, this type of approach works very, very well, because in this situation, once that we have a very nice control involving the L2, okay, and if once that we have the very nice control involving the L2 norm of the gradient, where in the L2 norm is fixed, these informations works together and permit to prove that this solutions has one estimate like this. That is, it is possible to find one constant capital M, such that if R is bigger and the mass is small enough, the L infinity norm satisfies this estimate, so we can fix R bigger than M, and we can conclude that our solution are, in fact, one solution of the original problem. So this is our approach. This is the one new idea, because here we don't use any geometric condition. We cannot ask that the nonlinearity is C1, and only we work with this situation here. For dimension 2, the approach, it's quite similar, okay? Because here we repeat the argument. Of course, when we are in dimension 2 and we are work with a critical exponential growth, the Trundick-Moser inequality works well when you have a very good information involving the L2 norm of the gradient of the sequence of one family of solution. And here, we prove that it is possible to get, because when the R, the mass R, is small, we have a very nice control involving the L2 norm of the gradient of the solution. This estimate is very, very nice because it permits to use the the Moser iteration technique or bootstrap argument. For dimension 2, bootstrap argument works very, very well in this case. And once that you have a very nice control at the L2 norm of the gradient, it's permitted to prove very nice information involving the L infinite norm. And again, we can conclude that our solution of the auxiliary problem are in fact one solution of the original problem. In whole space, okay, Rn, the approach is similar, but here we need to assume that the potential V is the N periodic, okay? Here, it's a very, very important to point out. When you see in the literature papers that work with this type of problem, 27, in general, the authors, when they work with this problem, with the situation L2 supercritical, the authors assume very hard geometric condition on the potential V because they use the Pohorjaeva identity. Here, we avoid the Pohorjaeva identity, so it permits to consider one large class of potential V. In our case, for example, we only consider the potential V bounded, Zn periodic, and the potential V has one positive infimum. Have this information, we can transform this problem in one L2 supercritical, L2 critical problem. We can use some result that I developed with another colleague from China, Xiao Ji, and we prove that the auxiliary problem associated with the problem 27 has one solution, and we use the elliptic estimate, and we prove that this problem 27 has in fact one normalized solution in the case where the dimension n is bigger than or equal to 3, and the dimension n is equal to 2. So finally, working to finish my talk, I would like to say that the existence of normalized solution for another domain, it's very hard. For example, if you try to get normalized solution in healthy space, we don't have the invariance of the orthogonal rotation group. In the healthy space, we need to have a careful, because the healthy space is invariant only in some direction and not in all directions. Recently, we proved the existence of normalized solutions involving healthy space. In hyperbolic space, we have recently one paper with Li Junchen, and we change Rn y the hyperbolic space, and we prove the existence of normalized solution. And now with another colleague in my department, Renan Sneri, we are using this approach to prove the existence of normalized solution on graphs, because the existence of normalized solutions in graph, there are only few papers, because on graphs, we have a lot of difficulties to use a translation, rotation, etc., etc. Okay, and here I have one slide with and some references. Okay, we have one very nice papers do it. Jian. Jian is the more expert mathematician in this subject. We have a very nice paper do a Bart and the other co-authors. Okay, and I finish it here. Okay, thank you very much.
Okay, thank you very much, Professor Claudianor, for your presentation. Some question, please. Again, thank you very much for your presentation. On a brief of seminar organization, you